Good afternoon, everybody. I'm Jean-Philippe Ponto from the University of Liège, and I will chair this afternoon session. So we have 7 presentations, and all the speakers have sent their presentation. That means there is no show. That means I will ask all the presenters to stick to the schedule, because if we delay 5 minutes for each presentation, well, we will end up without any coffee at the coffee break. So we will start immediately, and the first paper, the title is The Effect of Material Orientation on Void Growth, and it's proposed by Hosseini, Nieto-Fuentes, Dakshinamurthy, sorry for the name, Rodriguez-Martinez, and Vadillo. So the floor is yours.
Hello everyone, I'm now Hosseini from the Nonlinear Solid Mechanics group of UC3M. And first, I appreciate all of the participants for attending my talk. And also, I appreciate the organizing team giving me opportunity to talk in this great conference. Today, I will be talking about the effect of the material orientation on void growth. This is my presentation. Will be divided in 6 parts, and I will start by an introduction about ductile fracture in anisotropic material. Many materials show anisotropy. It can be road sheet, it can be printed metal, or any manufactured metal. And anisotropy simply means that the mechanical properties of material varies with the direction of material. That's the reason we are going to study the ductile failure in an anisotropic material. Here you can see the 3D reconstruction of the void in a metal. And in this picture you can see how voids are placed together. It's a typical way to make, for analysis, to make a periodic structure, and then analysis only one unit cell of this periodic structure. So in this case we have the same. And the matrix material around this void inside this unit cell is anisotropy, and its yielding is described by this function, which is yield 2004 18 parameters, which is proposed by Professor Barla. And it is defined by this formulation. Here we have principal values of stresses, and these principal values of stresses are obtained based on 2 transformation on the deviatoric stresses. It means we have this transformation tensor, and we have deviatoric stress. We do transformation, we obtain transform deviatoric stress, and then we obtain the principal values of this tensor, which has this formulation. And finally, the effective stress is defined by this formulation, and Kc is 4 here. Here, these tables are the elastic and plastic materials parameter, and here this table is the anisotropy parameters in year 2004 yield criteria. And having these anisotropy parameters, we can plot the yield locus in the deviatoric p-plane. And as you can see here, it's not circle anymore. It shows anisotropy. Here are the values for the yield stresses, and these are the angles. So this clearly shows the anisotropy, and the material is aluminum 2090 T3. And the yield condition is defined by this formulation, and yield stress is defined by the power law formulation, which is this one. And we have also used Newman subroutine in abacus and integration, a numerical integration scheme, which proposed 2020 by 21 by myself and my professor. And this is our finite element model, which is a unit cell and it contains a spherical void inside it. The void volume fraction, the initial one, is 0.0042, and we have 3 triactuality, 3 load parameter, and 86,000 elements in our model. And for loading, we have triactuality and load parameter. As constant, again, we use another MPC subroutine linked with UMass. Because we have a void in our material, so the microscopic values for stresses and strains are different. That's why we have to average all of the integration point in our model. So we average all of the integration point using this formulation and this formulation to obtain the microscopic principal stresses and microscopic effective stress. And finally, the effective stress follows this formulation and the effective stress follows this formulation. So let's go to finite element results. So we have 2 parts in our results. The first part is when the material axes align with the orthotropy axes aligned with the loading directions. So here are the material axes or orthotropy axes, which are x, y, z, and sigma 1, sigma 2, and sigma 3 are the loading direction, with sigma 1 is the major loading direction, sigma 2 is intermediate, and sigma 3 is the minor loading direction. And notation we use is like this. For example, x, sigma 3, it means x is aligned with the minor loading direction. Y, sigma 1, z, sigma 2. And we have the same pattern. We have 3, in fact, we have 3 different material orientation. X, y, z, y, z, x, and z, x, y. So here we have plotted the void volume fraction versus microscopic effective strain. And we have x, y, z, y, z, x, and z, x, y material orientation with 1 minus for triactuality 2 and load 1. And in the other one for triactuality 2 and the first one load 0 and the second one load 1. So as you can see here in this figure, for different material orientation, we have different patterns for void growth. And this highlights the effect of material orientation on void growth. In the second part of the results, we have one axis of the material orientation aligned with one of the loading direction, and the other 2 axes of material, which are here, for example, y and z, as a misalignment from 0 to 90 with the other 2 loading direction. So in the second part, we have misalignment between loading direction and material orientation. And here you can see the results for 3 different values of misalignment: 22, 45, and 67. I apologize for the size because I think you cannot see the small. As you can see, and we have investigated this plot for 3 different triactuality values. As you can see, in all of them, when triactuality increases, the void volume fraction increases. But another important result is that when the angular misalignment from 22 increases to 45 and 67, again void growth will increase in the material. I mean, in this picture you can see it better. The first one is for the misalignment 22 for the same microscopic effective stress, all 3 of them. The second one 45, and the last one 67. So you can see as misalignment increases, the void growth increases in the material. This is the 3D reconstruction of the surface of the void. And this is the 2D mid-cut of the void, plane of the void. As you can see here, when we have misalignment, then the faces of the unit cell are not straight anymore. So they are twisted here in this region, and the void is rotated because of misalignment. In this part, we have the effect of triaxiality. So we have investigated the calculations for 3 different triaxiality. And here is the void volume fraction with angular misalignment. Angular misalignment increases from 0 to 90 degrees. As you can see, the void volume fraction decreases with angular misalignment at the beginning, then it increases for 3 values of triaxiality. And these are for 3 material orientation, x, y, z, y, z, x, and z, x, y. And we have the same pattern for 3 of them. It means all of them, for all of them. We have a minimum in which the void growth is lowest. Here is the position of minimum, and for the other one is here. For different triaxiality, we have different positions. It's some intermediate values for angle, and the other one here. And we have, to generalize this conclusion, we have analyzed the same thing for 2 other materials. This is the materials I mentioned before. For 2 other materials, again, you see we have this minimum void growth rate for intermediate value of misalignment. And this is here I'm going to show the influence of load parameter. In the first one, in both of them, we have load 1 and 0, load 1 and 0. But the first one is angular misalignment 22. This one is angular misalignment 67. So you see in this one, for load 0, we have more void growth. But for this one, for load -1, we have more void growth. And this shows the effect of misalignment on the void growth. And we have plotted void volume fraction again with angular misalignment for 2 different load values. And again, you see this minimum void growth in an intermediate angle. Here, I'm going to show the influence of material orientation. So, we have 2 figures. In each figure, we have 3 material orientation I mentioned, and here we have 3 of them. But for 2 different angular misalignment. As you can see, if we compare these 2 plots, we see different patterns for each material orientation. For example, here, here the highest void growth is for 67 degrees. Here the highest void growth is for 22.
You have 2 minutes.
Okay. And here is 3D reconstruction of both cases. And here we have the same plot, void volume fraction versus angular misalignment. Again, you can see for 3 material orientation. Again, you see a minimum void growth in all of the curves. This means we can find an optimal material orientation and angular misalignment that gives minimum void growth for a given T and L. I don't read the conclusion, sorry. And this is the paper we published with this work, and I appreciate the European Research Council for funding this research.
Thank you very much. So we have time for questions.
Maybe one comment. Here you define the triaxiality as the usual way, which is the mean stress divided by the fundamental stress. If you define modified triaxiality, which is still the mean stress divided by your new function,
function,
then if you have tested the same modified triaxiality, then you get the same growth rate. You see, because in the different direction. Because if you are pulling in one direction, you have to apply different stress ratio to get the same modified triaxiality as in another one. So if you do that, you don't get an orientation effect. At least, I'm not talking about the disorientation at least if you consider the first calculation you showed, where you were pulling in the principal direction.
The problem is that we cannot define based on this yield friction because of complexity of this, we cannot find a closed form that to put. Also, this was, for us it was a challenge, and in any papers, we have seen at least they use the same thing for also anisotropic materials, and one of them is the paper of Middleman in 2015. In fact, we have the same problem.
Because we did calculation with this fixed, with modified reactivity, and then we can get all the curves collapsing into a single curve.
Honestly, I'm not aware of that. But for misalignments,
Misalignment is something different.
and the main point of this research is the misalignment, because for material orientation we didn't. There was also previous works on that, so the only difference for this work is the misalignment.
Okay, so let's